Hello, everyone, and welcome once more to the course on Introduction to Environmental Epidemiology. Today, we will have the first set of lectures on sources of bias and specifically on exposure and outcome misclassification. So, Beth, and I hand it over to you for the introductions of our speaker today. Thank you.
Hi, all. Thank you for joining us this April beautiful day here in Washington, D.C. area. It looks like our numbers are still ticking up, but I think we'll go ahead and get started. I'm very happy to introduce our theoretical lecturer today, Marianthi Kioumourtzoglou. Hopefully that was somewhere in the vicinity. Marianthi has been a very active member of ISE, and we're very lucky to have her here today. So thank you all, and I'll turn it over to you, Marianthi.
Okay, great. Thank you, Beth. Thank you. First of all, a huge thank you to Anna and ISE for setting up this course. I think this is a fantastic idea, and I'm very glad and honored to be invited to speak with you all. And hi from the very sunny and warm Louisville, Kentucky, which is where I am now, and I'm in a nice clubhouse, hence the interesting background for a meeting. But all that said, I do not have new slides prepared for today. I thought we'd have a discussion. I'm assuming that you've all watched the video, and I'm up for questions and discussion. And if you mentioned, like, most of exposure measurement error studies are on air pollution, so I'm also very happy to discuss other potential examples about how we can conceptualize things, or if no one has anything to say, I can just keep talking for the next 30 minutes by myself, which is very easy for me to do. I do think it's more fun if things are more interactive. So if you feel comfortable, obviously you don't have to do that. If you feel comfortable to turn on your cameras and speak up, that's fantastic. Obviously, don't worry if you're not feeling that today. So exposure measurement error is something that we cannot avoid. It's pretty much impossible to conduct a study without any exposure measurement error. We can develop smaller studies that have less error, so we can try and minimize exposure measurement error with personal monitoring, for example, in air pollution. Or if we want, we can have multiple biomarker biosamples rather to analyze for biomarkers, but most of environmental impacts are at the individual level, have quite low effect estimates, so we need big numbers. And there is obviously the balance between, okay, if exposure measurement error, as you all saw in the video, tends to, for the most part, attenuate effect estimates, then if we had, and assume for now that it did nothing to standard errors, and it depends, on what can do to standard errors, on whether it's classical or if it's Bergson. It's never really one or the other. It's always somewhere in the continuous. But if you can imagine, if you have a point estimates that very close to the null, then the standard errors are more likely, even if they were exactly the same, to cross the null versus if we had conducted a study with improved exposure measurement, exposure assessment rather, so smaller error, in which case that same effect estimate was going to be further away from the null, and so would its standard errors. So it's this balance here of, do we prioritize better estimates over do we prioritize sample size? And in sample size, then also we need exposure, three things for power, right? Sample size, effect estimate, size. and exposure variability. So that depends on the study and the possibility. If I wanted to study, for example, long-term effects of air pollution exposure, it's pretty impossible to follow people with personal monitoring for years and years. Ideally, we would like, and my internet connection is unstable, so if I go off at any point, please like make sound, like, or text me, or on the chat rather, so I know that that's the case. So I think that's how I wanted to start, and saying that there are all these things that we should think about. In the literature, for the most part, what people do is most often, well, actually many cases, people will completely ignore exposure outcome, measurement error outcomes classification. But most commonly, if the issue is acknowledged, it's acknowledged as one sentence in the limitation. Yeah, we most likely have exposure measurement error. It should bias the results to them null because it's likely non-differential. Which is great, but it's always, it feels like an afterthought. Also, I think we've been using non-differential more freely than it might be the case. So does anyone, it's 45 of us in this room. Thank you all for joining. Does anyone remember and would like to share with the rest of us the difference between differential versus non-differential exposure measurement error, please?
Feel free to put that in the chat if you'd like, or you can raise your hand icon.
Yes. And also, like, I won't wait here for someone responds, but please do respond. So I know that they at least. Okay. So differential versus non-differential error or misclassification. Again, okay, one step back. Error for continuous variables, misclassification for binary or categorical variables. So with that in mind, non-differential exposure measurement error means that any error or misclassification, if it's a categorical exposure, and the exposure variable does not depend on the outcome. So for example, that would mean if I'm looking at the effects of fine particulate matter on cardiovascular disease, it would mean that, oh, thank you, Lillian. So differential, there are differences in cases and controls about their exposure. Correct. Yes, exactly that. So back to my example, if I'm looking in a cohort study, PM2.5 and cardiovascular disease, the effects of PM2.5 on cardiovascular disease, then I should not have different amounts of error by vulnerability for cardiovascular disease, by risk factor for cardiovascular disease. So people who are more likely to develop cardiovascular disease should not have higher error in PM2.5. If they do, that's differential exposure measurement error, as Lillian said. But if, yes, there is error, but the error has nothing to do with the outcome of interest, then that's non-differential. And conversely, outcome misclassification would mean differential outcome misclassification means that misclassification in the outcome depends on the exposure. So I have more error in my cases, for example, versus my controls if I'm in a case control study. And non-differential means that, yeah, I have misclassification in, the hospitalization codes I use for my time series studies, but it does not depend on temperature levels, if temperature were my exposure. Non-differential exposure measurement error is the situation where we want to be. A non-differential exposure measurement error, if the error continues, would bias towards the null. If the error, if the exposure, or conversely outcome, is binary, so misclassification in a non-differential misclassification in a binary variable would bias to the null always. If categorical, that would not be the case. It depends on the error structure. Is there a typical reason why you would have differential? Excellent question, Jennifer. Thank you very much. And I did not go over this in the video, but I'll go over this now. We are starting to see, for example, with temperatures and air pollution warnings coming up. This had not been traditionally the case in our studies historically, but right now, if let's say I were pregnant, I'm not pregnant, but let's say if I were pregnant and I know that I'm already at a high risk, then I get a warning in my phone that AQI today is over the roof, I may be more likely to change my behaviors to protect myself. And so that would mean that I would decrease or increase, again, it depends on what those steps would be, my error just through behavioral changes because I got a warning and because I got worried because or I'm at high risk of heart attack or whatever, right? So I do think we will start seeing more differential measurement error issues. We are currently, and I saw Vijay is here, who is my postdoc, so you can ask him questions if you'd like. We are currently running some simulations to quantify the impact of differential exposure measurement error on air pollution and pregnancy outcome studies. Stay tuned for that. We're still, so far, it looks like the situations that we've simulated also go towards the null, but that's not, we need to check more scenarios and make sure that that's the case. And also that does not necessarily mean that that's how it would translate in other exposures for differential error. The other thing is if you had, for example, biosamples in cases and controls, and you did not mix case and control samples together. So you analyzed in the lab all the samples from the cases versus all the samples from controls, and there were some batch effects or some instrumental thing on only one of the two batches, right? So that would induce differential error by case status. Or if I'm looking at a neurological outcome and I am at a, urban areas have higher air pollution levels, but also higher density of neurologists. And, people may be more likely to be diagnosed better and earlier with something, right? So all these are situations that we do need to think about. And the other thing that error can do is induce or make appear effect modification when there is none. So if you can think that the error varies across levels of the population of interest. So for example, if you are looking at effect modification by age, air pollution, again, the example, sorry, I'm using too much air pollution examples, but that's my area of expertise. So, but do ask me about other examples. Oh, Alan, hi, Alan. Yes, you have raised your hand.
Can you hear me?
Yes.
Yeah, great. Hi, Marianthi. Yeah, I was wondering in the case of mixture and modeling, can we take account for exposure measurement error? Because I think we're like looking at effect as a mixture. So, and for example, if we're measuring air pollution, the case of air pollution again, but for example, NO2, black carbon, PM2.5, you are modeling like using like different modeling approaches, and you have like different exposure measurement error. So if one of these chemicals, air pollutants, pop up in this mixture analysis, can we really trust on this, or is there is a way of accounting, or just like try different sensitivity analysis and
that's an excellent question. And in that case, yes. So as you said, different things may. So for example, take NO2 and black carbon, like they're both traffic emissions related proxies, surrogates, and it's possible that they are measured or predicted with different amounts of error. So in theory, they should be correlated. I may identify associations with one, that it's not the important one just because the other may be the important one was measured with more error. So you're absolutely right. There are ways to think about it. What I would say is, even in single pollutant analysis, exposure measurement error correction is not exactly widely adopted yet. So I don't think it takes. I know there are groups working on exposure measurement error correction methods for mixtures, but we're not there yet, and what level of information we would need is tricky. So I think for now, sensitivity analysis, and try to understand, like, for example, there are so many papers that for air pollution, they do not even provide the cross-validated R-squares from the prediction models by pollutant, right? And then not even any discussion. Yes, we found associations with this pollutant, but actually it wasn't predicted very well. So, we're more cautious about these results. Or we saw this very strong association, and that pollutant actually had very excellent predictive accuracy. We had excellent predictive accuracy for that pollutant. So that makes more sense. So we definitely, as a first step, need more discussions like that in papers, and when we are even in our own papers trying to think about our results. And as you said, sensitivity analysis. I don't know what the sensitivity analysis would be. For example, I've done a paper, and Marc was with Marc, who's doing the application right after me, and we were looking at air pollution, pregnancy loss, and we had monitoring sites in Boston. So we had the full population as the main analysis, and then the sensitivity analysis restricted to people living closer to the monitors. Yes, that should have reduced exposure measurement error for those people, one. But two, the characteristics of that subpopulation could be different, right? So people who live in the urban core may be different than people who live at the suburbs. So the differences in effect, the change in effect estimates that we saw, does it mean that it was the error, or does it mean that it was some effect modification that we were capturing from some, probably a combination of both, but we don't know, which part contributed more, right? So sensitivity analyses are great, but oftentimes it might not be easy to interpret the results of a sensitivity analysis. So different ways of sensitivity analysis that would get to different things might actually be better. So if you, I don't know, crazy idea, like try to match people in the suburbs versus closer to the monitor by some propensity score, and then the results could be more interchangeable, not interchangeable, but the populations exchangeable, so the results more comparable. There you go. That's what I wanted to say. Jennifer says, if there's a thematic or behavioral reason that there is a difference for a certain population group, can we control for this in the model to make the error non-differential? That's a good question. I don't know that we would. So first of all is how do we have this information? Do we really have this information? Oh, excellent. So Marc will give the response for me. Thank you, Marc. But I do think it's important, yes, to start thinking of what type of information you have. And when we don't have the information, my go-to is simulations always. It can help, it cannot hurt in any case. Whenever in my group we're not sure about which way something would go, we always run simulations. They not always make it into the papers, unfortunately, but sometimes they do, and that's always a good, starting point to see which way you're going. Going back to the impact of error that I was talking earlier on exposure misclassification, on effect modification. Sorry, I woke up very early today and I'm not a morning person, in case you don't know me. So if, let's say, we want to look at the effect modification of age on PM2.5 exposure and, I don't know, some outcome, an asthma attack or blood pressure, and I have all adults in my study, but adults are from, you know, potentially students, undergrads to, you know, 80-year-olds, and obviously everybody has very different mobility patterns in the city. At best, we can assign exposures at the residence, right? So we are actually, if we assume that the retired population may be more likely to stay at home or around their house versus a younger population who that is more likely to go to school, go to their jobs, go, you know, out at a different location in town for fun at night, then we may be capturing the exposure of the older people better. So that's something that I have not seen discussed a lot in papers, but it's definitely another issue that exposure measurement error can have in the analysis. So not only biased effect estimates, not only potentially biased inferences, but also it may make something look like an effect modification, or it could mask a true effect modification. If, for example, in the example I gave, the effects in the younger population are stronger than in the older, the true effects, but we measure with much more error the exposure of the younger population, then the error would bias the effect estimate in that subpopulation, which may then make the effect estimates more similar to the estimates in the older population. So that's something that we should also keep in mind when we're thinking about effect modifications. With bias samples, that might be trickier, unless again it's a batch issue, right? If I analyzed all samples from males in one batch and all samples from females in another batch, and, you know, there was something that some batch effect there, that might be an issue as well. But as someone who has never been in a lab, I would like to think that people mix things up a lot before analyzing them in batches. But I'm not sure about that, actually. Have I answered all questions? Is there any other question that people have? I think.
Could you talk a little bit about, you know, with non-differential misclassification or error? Are we always comfortable assuming that the bias is towards the null in that situation? Or are there
No.
situations where that wouldn't be true?
I think there can be situations that is not true, right? So if, for example, I have a lot of error down at the lower, if I have more error at lower exposures, and also the healthier populations are at lower exposures, and then I have less error going up in the exposure, but also higher exposure, more vulnerable people live at higher exposure, right? That's differential exposure measurement error that I think could make things go the other way. So I don't think we're comfortable. We should be comfortable when it's differential. I think when we assume that the error could be differential, we should try and think much more carefully about the magnitude. We are always thinking about the magnitude, but also the direction. Marc says, I think it's also dependent on the true underlying. Yes, so that is true. And it is likely that exposure measurement error will change the exposure response curve that we're seeing, right? It could flatten out the parts of the exposure where it's more error. But that part is not necessarily about, this can happen if error is non-differential as well, right? So if, say, I have more error at lower levels, then I might start slower and then pick up a lot. Or the other way, if I have more error at higher concentrations, then I may start steeper and then level off. Marc.
Yeah, sorry. Hi, Marianthi.
Hi, Marc.
Right. So what I was thinking, and I'm not sure whether that's what you were getting at or not, is that if the actual dose response, the causal dose response kind of is like some, comes back down at higher levels, then you can get strange, you can get things that don't necessarily bias towards the null, depending on where you are on the exposed dose response curve, no?
If differential or non-differential?
No, non-differential.
So it's a bias to the null. What you're saying would be more interesting if it were a bias in the absolute direction, right? But measurement error is a bias to the null in this, if non-differential. And it's always with respect to the null, not in absolute sense. So
No,
it would flatten out. Yes, but you're right. It could flatten out certain parts of the dose response.
Well, but I mean, if the dose response actually is curved, right? So if the true dose,
the true one,
comes
yes,
down at the highest levels, then those highest levels could actually get biased up if you're moving someone with a lower level into that higher level. So in the sense of, it's easier to think about in terms of categories, right? So if you've got categories of exposure, and it's sort of
never easier to think in sense of
categories. No, you don't like categories.
Sorry, go ahead.
But if for a moment, if you indulge me, and you've got like 5 categories of levels of exposure, if the underlying true causal effect is monotonically increasing, so always going up, then if the bottom one is your reference, the top one can only be biased towards the null. But the internal ones can go either way, right? Because you're mixing up exposure levels, so something in the middle, you can mix up something from higher or something.
Yes, correct. So that's why for categorical, it's not necessarily to the null. For binary, it's always to the null, but not categorical, because it depends. Yes.
Right. But if you think of those 5 categories, and now if the true underlying response goes up to the 4th and then comes back down in the 5th, now that 5th could actually be biased upwards, because you could be misclassifying someone from the 4th into the 5th category and moving it up. Right. Now, I don't know how that plays out in a continuous exposure, if the true underlying
yes, yes, because exactly. So that's what yes. So for categorical, I agree. It's not always to the null. It depends where you build people given exposure. But for continuous, the part with the more error, that part would move, if non-differential, likely more to the null.
Okay. Yeah.
So it wouldn't seem stronger at that part, but you'd miss potentially that association, or that might make the association look nonlinear, even if it weren't linear.
Right.
Correct. But now, if on top of that you have differential error, then is where, but I would say, and I don't think I said it in the video, if you don't have an association, if there's no true association, error itself will not make, differential or non-differential, will not make an association appear. So
wait,
if you see it.
Yeah, right.
Yes. So if you see an association, you may not be sure if it's biased towards or away from the null, depending on whether the error is differential or not. But error itself will not make an association appear. Now, error itself, in combination with confounding and other things, might induce a bias that makes an association be there when it's not. But if we've done a very careful job at making sure that there are no other sources of bias, then error itself would not make an association appear.
You're right, and you're making me realize that one of the things in the slides I'm going to present is probably wrong but I will therefore, but clarify, because this is a tricky point. I mean, what you're talking about when you're talking about differential, I think, right? When you're saying differential measurement error, you're saying that the error is different by the outcome, not that the measurement is systematically one way or another by the outcome.
What's the difference between these two?
Are you saying that differential would be if you have, let's say, cases and controls, and in your cases you have more error and less error in
That's
your
differential.
versus because the other differential would be that in your cases you're always measuring a bit higher, and your controls you're measuring a bit lower, right? That's another
So,
form
but
of
that's still error. No, exactly. When I say error, it's not automatically random error. It could be systematic error, as what you're saying.
Okay, but if it's systematic error, then if it's differential, you can create an association where there is no true one. Because if you're differentially measuring cases higher, it's going to look like the exposure is related.
Yes. That's if you. Yes, that's true. If you always keep cases a 5 and controls always have a 0, but that 5 is a systematic error and it's not random. Yes, that is true.
All right. That was a really interesting discussion. Thank you. It looks like we have one question. It is time for us to sort of transition over, but since we're talking about
Marc,
right
do
now,
we have
I
your
think we could
permission
jump
to answer the last question?
So
Sure,
it
absolutely.
says, so what I got from the differential error, by having a good design, we can decrease the risk of having it. For example, processing controls and case samples in the same batch instead of doing it in different batches. But how can we decrease the risk of having a non-differential error?
So we can better assays if we're in a lab. So it depends, different stories. So if I have as bias sample something that's more reflective of the exposure response, for example, many DCs have very short half-lives, right? So if I take my urine sample now and analyze me for phthalates, that's my last 6-8 hours representative. How well does that translate then if you want to see, long-term exposure? So and that depends also on exposure patterns. Like if I'm exposed consistently, then it won't make much of a difference. But if I'm at a hotel now and I use a different shampoo, so everything is different, right? So I think depending on your exposure, there are ways to assess exposure better. So for example, if we have air pollution, try to build, better prediction model. Now you may say, but I'm not in the area of building prediction models, and I don't have easy access to people who can build a very good prediction model for my specific area of study that maybe doesn't have something existing. So I don't think we can guarantee, but there are ways to try and minimize it. And at the very least, if there's enough money, we could always try something better in a smaller subpopulation. So like a small validation study. So let's say, again, going back to the phthalate example, we have a population of 500 people, but for maybe 20 of them, we get repeated measures or things like that. Or if I have an air pollution study and I can afford to give 10 participants a personal monitor for a week. And then that could help me at least understand the magnitude of the error I have. But again, that needs more money, and that's not easy to get these days.
Great. Thank you so much, Marianthi. That was great.
Thank you.
That was a great discussion. And we're going to, I think, transition at this point over to our practical application of thinking about misclassification. So I'm, again, very pleased to introduce Marc Weisskopf. We're very fortunate to have him talking to us about this topic. And I'll turn it over to you, Marc.
All right, thank you. So let's see. Let me share my screen since I do have slides.
Sorry, also, Mark, I just realized in the discussion that we just had.
Yeah.
That's a thematic different. No, never mind. Okay, yes, go ahead. Sorry.
Okay, chime in anytime though. All right, let's. Okay, so I'm gonna. I guess the title is accuracy and validity trade-offs, and that's sort of the topic of the paper that I gave everybody. By the way, thank you again. It's great to be able to do this, and thank you to Beth and Anna and Infinity and everybody for all the work going on behind the scenes to make this happen. This is great. And I think, as they've said, we'll try and answer questions and do things. Feel free to chime in or put things in the chat while I'm talking, but also, I guess, if there are questions that come up later or we don't get to for any reason, I guess there's a more offline way of continuing the discussion. So check out that if you need it. Okay, so so the main talk is the main portion is this accuracy and validity trade-offs when we're considering measurement error. And that's the topic of the main paper that I gave you guys. But I'm going to touch on a variety of other issues also. So we'll just get to those. But okay, so the first thing that I want to point out is, right, we're in this sort of era of the exposome and epidemiology where we have, unbelievable ability to measure all sorts of things in fine detail from a single blood spot or even externally in different environmental samples, et cetera, to get, really personal exposures from airspace, silicone wristbands, all, blood things, Fitbits, all this kind of stuff. It's a wealth of data that's an incredible resource. But we also have to think about what that means when we take that data and put it into our epi studies and how we work with that. So I think Marianthi talked a little bit about this in her recorded talk, but this is just sort of a conceptual model, right, for exposure-related disease with the idea that we've got sort of two compartments, two boxes by the dashed lines. One is external to the body, stuff happening out in the environment, and the other is internal inside the body once it gets sort of into the envelope of your body. And as we think from environmental health, we really need to think across this whole spectrum from the place where some exposure is emitted or comes from in the environment, kind of how it moves through the external environment in media, how that media transitions to sort of microenvironments around an individual to lead to actual personal exposure. All of this is really important because, when you think of a risk framework kind of thinking, you could have an incredibly toxic compound that's emitted somewhere, but if it never gets in contact with anybody, the risk from it, from a health perspective, would be low, even though it is incredible. We know from other studies it would be tremendously toxic. So we have to really understand this on many reasons to know what we have to be concerned about, and also how it gets to a person to sort of model that exposure. How much is someone actually getting exposed to? And then, so that personal exposure then basically leads to internal dose of some toxicant through pretty much inhalation, ingestion, or dermal. You could also poke something in directly, I suppose, but the main ones are inhalation, ingestion, and skin contact. And that then crosses into the actual body where you have absorbed dose. Presumably that goes to a target tissue somewhere of whatever disease you're concerned about. In my case, it's often the brain, so it's what's in the brain, and that somehow alters the structure and function of the brain, leading to some disease endpoint eventually, right? And so we think along this line, we have many places in here where we could measure things to get an exposure estimate for somebody. For example, polybrominated diphenyl ethers, those flame retardants, right, compounds. We could take a blood sample and measure how much gets into the blood of somebody. We could kind of collect people and do hand wipes, what's on their skin. Dermal is one way that it could get in. And so if we know that it's on their skin, that gives us an estimate of how much might be coming into a person. So it's sort of in that very personal exposure realm. Or perhaps we could go to people's homes who are in our study and take dust samples and say, what's the level of PBDEs in the dust samples as some measure of what they are likely exposed to, right? Another example would be air pollution. We've just talked a lot about. We could have personal monitors, right? You could do a study where you put backpacks on everybody with a pump in there and put the, the intake for that pump in their breathing zone. So you get sort of 24-hour as they're walking around, what's in their breathing zone as a pretty personal measure of whatever air pollutant they might be taking in. Or you could put an air sampler in their bedroom and say, most of the time they're in their home, and that's going to roughly reflect the exposures they're going to get. So, and it's simpler than outfitting someone with a backpack constantly. Or we can do the kind of thing Marianthi was referring to, and we can kind of build these spatiotemporal models of wherever you are in the United States or in Europe or any part of the world. If we can build a model of what ambient levels of particulate matter or any kind of other air pollutant is, we can just sort of assign you an exposure based on where you live and say you live in a higher air pollutant area, so you are probably going to have, in general, more air pollution exposure, right? So I can kind of rank people based on their residence. So now in doing that, of course, given the discussion we've just been having, what's kind of obvious, I think, hopefully to all of you now from what you've seen in Marianthi's talk and other stuff that you've done, is that as you move to the left in this schematic, right, away from the target tissue and the altered structure function and move out absorbed dose, personal exposure further towards source emissions, we are probably getting more error, measurement error, in what someone is actually exposed to, right? So we can probably agree that if you take a blood sample for PBDEs, you're probably going to get a better assessment, a more accurate assessment of what's in that person at the time you take the blood sample than if you, gathered dust from their home and saw what the PBDE levels were in the dust in the home. Or if you put the backpack on somebody for air pollutants, you're going to get a much better personal assessment of what they were exposed to as they walk around, because you've got it right with them all the time. Then if I simply build a model and say, I know where you live, and based on where you live, where I think you spend more of your time, I can say you're in a higher air pollution area, so you probably got higher air pollution exposure. Clearly more error involved in that kind of an assessment. And as we've just been talking about, and Marianthi has been giving her talks about and talking a lot about, that is more error typically biases, we think, towards the null in most cases. So that's the risk we run, is that we have a lot of bias to the null. And so the risk is we miss an association that is really a true causal effect because we've biased it to the null. So that is a problem, but if, here's just a schematic of making an air pollutant exposure model, right? We can do that based on monitors. This is the United States, of course. So monitors all across the United States, EPA monitors, other people's monitors. We can see what's actually measured in certain places. We can combine that with geographic information, how far any spot is from a roadway, what's the population density there, what are sort of known other sources, meteorologic data like wind speed and all this kind of stuff, and build a predictive model for literally any spot in the United States. And people are doing this around the world, of course. There are many of these kinds of models. The bottom is New York City area. You can get down to that fine detailed level, and I think you can probably see what looks like a road network there. That's not because we've superimposed the road network there. That's because those are high spots for, in this case, PM 2.5 or particulate matter 2.5. So the model predicts pretty well. It says if you're right on the road, you're going to get higher particulate matter exposure, right? So the question is, now we know this is not as good as putting a backpack on somebody. And if you're in my study and I simply assign you a PM 2.5 level based on where you live and this kind of a map, it works reasonably well. It seems to pick up things that we think, but it's not going to be as good. It's going to be less accurate, more measurement error than if I was able to put a backpack with a pump on you for the entire duration of our study, whatever we're trying to do, and just monitor what you're getting when you walk around on a daily basis, right? So in general, we prefer getting a more accurate value, a more accurate estimate of the exposure someone has, because we have less non-differential measurement error. Hopefully we'll get into the differential part, but even if it's non-differential, we have less of that. So we have a better chance of seeing a true association, a true causal effect, if it really is there. But what I want to talk about is that there are trade-offs when we do this. So imagine that study where somebody is wearing a backpack 24/7 and has, the intake in their breathing zone. So we get a very accurate estimate of what they are being exposed to over whatever time period we want them to wear the backpack. But what we also have to recognize is that their own personal behavior is going to affect that exposure level. Now, it still is an exposure level, but it means if I'm somebody who, when I exercise, I go run along the side of a roadway, or I commute in my car on a really polluted highway, that's going to give me more exposure to whatever, to PM, or pick the pollutant, right? So personal behaviors, my physical activity, how much my breathing rate, my, in this case, even smoking, because the smoking might contribute to PM that's in my personal space. So lots of personal behaviors can affect that individual personal level with the backpack that I'm getting. And that raises the problem that if those personal behaviors are also related to whatever outcome you're looking at, you have traditional confounding, and we need to worry about that, right? So this is not no longer in the realm of measurement error. This is just simply confounding. And so in any study you do, you have to try and adjust away, or somehow design away or adjust away all of these personal behaviors that you might have some concern could be related to the outcome that you're looking at. And we do that. That's what we try and do in epidemiology, but it can be difficult. And sometimes you can't measure these things very well. Sometimes you don't know what they are, so you don't even know that they're there. Or maybe you know what they are and you want them, but they're not in your data set and you just don't have information on them. So you run a real risk of having a non-valid association, meaning not indicating the true causal effect between the personal exposure and the outcome, which we assume goes through the personal pollutant exposure affecting the target tissue, or leading to target tissue dose of something, and then affecting the outcome. But this directed acyclic graph, by the way, I blew over that too. I'm sort of using directed acyclic graphs, or DAGs, and I don't know whether everybody has familiarity with those, but very quickly, it's just trying to show
Mark, our last session did talk about DAGs, so we have a little bit of an intro. Yeah.
Okay, great. If you want more on that and you want to go deeper on that, if they didn't already tell you, I would definitely highly recommend Miguel Hernan and Jamie Robbins' What If book. It's available for free on his website, so you can look that one up. But so what we've got here in our DAG is clearly confounding. So I've drawn it as if there is no true causal effect between personal pollutant exposure and the outcome, but you would see an association because of confounding by personal behaviors. We can try and adjust them away, as I say, but that can sometimes be quite difficult. So the point that I really want to make is, what happens if instead of that backpack and that very personal exposure, we use that spatiotemporal model, the model built on all this external stuff like monitors around the country and wind factors and stuff like that, right? That, we hope, predicts personal exposure, right? That's this arrow here. But if hopefully you got in the DAG lectures we had that in this case, we've got personal behaviors pointing into, they affect your personal exposure. The ambient pollutant estimate affects your personal exposure. But very critically, the personal behaviors do not affect the ambient pollutant estimate, because it's derived and designed totally independent of whatever I do. It doesn't care how I commute to work, and it doesn't care what my physical activity level is or whether I smoke, right? So all of those personal behaviors that can be sort of problematic potential confounders of a personal exposure like this are not for the ambient ones. The personal pollutant exposure acts as what we call in DAG speak a collider, right? And as long as you don't condition on a collider, you block the path through the arrows that point into the collider. So you block this path through personal behaviors. So the only one still available is through a potential effect on target tissue dose and then the outcome. And so if you still see something, you know it is not confounded by these personal behaviors. So you're making this trade-off in the ambient pollutant estimate is not as accurate. It's got a lot more error in it, and that is definitely a problem, and it can bias to the null. But it is free of a lot of potential confounding of a much more personal exposure type, right? And it's free of this, even if you don't know what these things are, right? So that is a huge, huge advantage of moving to a more proxy a more proxy exposure like ambient pollutant estimates, it doesn't matter, how much time you spend at home. It doesn't matter how you get to work, et cetera, all those kinds of factors. It's no free lunch, right? Because it isn't totally devoid of potential links to the outcome. There may be other ones that I've depicted by the L here. However, these may be a little bit more known, right? I mean, we know how we built the ambient pollutant estimate, so we know what goes into that. So we have a pretty good handle on what things affect it. And of course, things that might be related to the outcome, these probably tend to be things like socioeconomic status, right? Variables that predict where you live, and where you live is related to exposure levels and might, for other reasons, be related to the outcome. So we do have to be worried about those kinds of things. But we don't have to be worried about these personal ones. So I tried a while back to kind of go through the literature to say, do we see examples of this anywhere? Can we see like concrete examples where these things don't seem to be affecting things? And I pulled a few that we have here. So this is I'm essentially trying to compare study results when someone uses an ambient estimate and does or does not adjust for personal factors. So these are studies that use a sort of more proxy estimate of exposure that's got more measurement error. And then they show results when they do or do not adjust for these kind of personal factors that, according to this DAG, should not lead to a biased association. This is one from Beata Ritz and all looking at air pollution and preterm birth. They got their air pollution ambient measure from sort of nearest monitor, what was the levels at the nearest monitor. And when you compare the results without adjusting for personal factors like smoking, alcohol use, and marital status, they saw what we see on the left here. And while there's a very, there's a moderate shift, but tiny, really. And so, is this actually confounding or just statistical bouncing? Not totally clear, but it doesn't change much when you adjust for things that are, can be very strong predictors of her outcome here. Another one is Monrad et al. From 2016, looking at traffic-related pollution and atrial fibrillation using, again, a dispersion model. So that's kind of one of these, more proxy exposure measures. And the other personal factor adjustment were things like, hours per week playing sports or smoking or alcohol consumption and BMI. And effectively no change whatsoever in the results when you adjust for all these things that are undoubtedly related to atrial fibrillation. Another one is Anne Aschengrau. She built these models that can estimate how much tetrachloroethylene or PCE that you are exposed to based on water distribution systems in cities in Massachusetts. And she looked at did I not put the relation there? Oh, congenital anomalies, right, related to that. And then there wasn't a whole lot of extra adjustment, but parental ages was one of them, right? And again, here, no change whatsoever. This was one I could pull out of the paper, but they also mention no effect of adding smoking or alcohol. Again, that would fit the theory. These are all these personal behaviors that shouldn't affect the water distribution system and how they model it. So it doesn't introduce confounding. And the last one from the Nurses' Health Study, Jamie Hart and others looked at particulate matter 2.5 and all-cause mortality, again, using one of those spatiotemporal models, and then went back with her to say, well, what happens if you do or do not adjust for smoking, which is obviously a big risk factor for mortality. And again, very little change in the hazard ratio related to the PM levels. So in general, these things sort of suggest what we're saying, and the theory is that if you're using these more proxy, more measurement error prone measures, you may be getting bias to the null, but you're avoiding what looks like you're avoiding a lot of confounding of these kind of personal behaviors. So some key points about this. The examples I just gave you, they're not proof, of course, of this concept, because it's possible that the variables we looked at in and out are not actually confounding personal exposure. The studies I showed you didn't have personal exposure measures. It would be really nice to have some studies where people have both the personal and the more proxy ambient one and say, okay, is the personal, does it look actually confounded by something? And then what happens when you use the more proxy one? So that would be a nice thing to do. And then, of course, you can't, to avoid confounding, it has to be something that does not affect your more proxy exposure measure, the one that's further away with more measurement error. So that's depicted here by the personal behaviors not having an arrow to the ambient pollutant estimate, right? So anything that has an arrow into the ambient pollutant estimate could confound, and you do have to worry about. Let's see. Yeah, so then the very important point here, did I not have that on there? I meant to put a circle on here, right? This more, or maybe it's over here. I don't remember. The more proxy measure here, right? The ambient pollutant exposure estimate has to have some correlation with your personal exposure. Obviously, if it has none whatsoever, then you don't even have an arrow here and you can't use it as an exposure metric. But also, if it's just really bad, then you're going to have so much error that you're never going to see any true, even if there's a true causal effect, it's going to be extremely hard to see if the error is really bad. So there's a lot of work that needs to be done here to understand how good is your, how much error are you talking about, right? So studies, environmental health studies that look at whatever measure you're using and assess in a, totally independent of the health outcome, but before you even get there, assess how good is your measure? How much measurement error do you have if you had some kind of other more gold standard, maybe there isn't a gold standard, but a better personal measure? How well does your more proxy exposure measure predict that? Because again, that's going to contribute dramatically to whether you can actually see anything, how much measurement error you have. And actually, if you know that, as I say down here at the bottom, there are these methods to sort of de-attenuate an effect estimate from, what the exposure, the bias to the null is from exposure measurement error. There are approaches to try and say, I know how bad my exposure measure is. I know how much measurement error there is. If I account for that, how much stronger would my effect have been? So you can do things like that. Yeah, so in the end, it's this sort of balance. You have to decide which sets of confounding, these L, if you're using an ambient one, or the personal, are you more concerned about driving your confounding? And which ones do you think you can better account for? To decide a little bit on which type of exposure measure you want to use. Yeah, I should also say that, I've not talked all about physiological factors here, but the same thing goes here. I mean, you can have internal, like, enzymatic differences between people that might be related to the outcome and how much you measure even at a target tissue, that can lead to confounding even if you had a target tissue dose, right? And in that case, the personal pollutant would avoid that kind of confounding. So at each step along the way, the exposure measure may rule out certain types of confounding based on what is and what is not a collider. So you can think of that at different points. And of course, at any point, the things that would confound a more proxy exposure measurement, so the L's here that confound the ambient pollutant measurement, they also confound the personal pollutant exposure measurement, right? So you might still have to adjust for these L factors, even if you use a less error-prone exposure measure. Yeah, that's that one. One last piece on this, just to raise, is that this kind of using the proxy thing also is relevant if you're concerned about reverse causation, right? That something about the disease is affecting the measurement that you're making. Also, by the way, I see the chat here, but I'm not following it as closely. So maybe people should flag whether.
Yeah, I'll chime in if you need to answer
Okay,
anything,
yeah,
Mark. I
let me
think
know if
you
there-
are answering as the question was.
Okay, great. All right, just yell if I'm missing one that I need to respond to. So anyway, this also, using a more sort of proxy measure, also helps with reverse causation, because reverse causation is something like you do a case control study and you get people with a neurodegenerative disease and without a neurodegenerative disease, and you measure like persistent organic pollutants in their blood, right? The problem there is that if you've got a lot of wasting or fat loss from the neurodegenerative disease, if a lot of those persistent organic pollutants are in the fat, as you lose that fat, they're going to get dumped into the blood. And so you could get a higher level of persistent organic pollutants because the person has the disease, not because they had more exposure prior to the disease. But again, whoops, if you, what just happened there? Why is that not working anymore? There we go. If you use a proxy measure like exposure based on occupational history, that is totally independent of the disease. So it has no arrow from your exposure into the disease or from the disease into that exposure. And so it is not affected by this reverse causation. And we'll come back to that a little bit later. Okay, just checking on time here. Great. Okay. So the final thoughts of this, on this aspect of it, right, is that more proxy measures, meaning more error further away from the tissue that you're concerned about, can eliminate some sets of potential confounding and reverse causation, but it only avoids that for any variables that don't contribute somehow to your proxy measure. So you have to pay attention to that. Bias to the null, what we've all been talking about this whole time, is absolutely an issue. So your proxy, your worst measure of exposure, still has to have some, and ideally as much as you can, relation to personal exposure. And that's a sort of study topic right there. You need to understand your exposure measure. How well does it predict personal exposure to know how much bias to the null you may be getting? And again, yes, if you understand that error, you might be able to de-attenuate. And again, studies that would sort of collect it, personal and ambient exposure measurement would be great, because then we could actually sort of directly test how much one thing is confounded and another is not. Okay, so now I'm going to shift a little bit. Now, this was something that came up a little bit in the question about multiple pollutants, you know, and not measuring them all the same way. And so this was one of the things I did want to talk about, you know, effectively co-exposure confounding, right? So what happens if you have different measurement errors on different exposures, which I think was that exact topic, right? So stepping out of air pollution and thinking about like mercury exposure, metals for a moment, right? Here's an example I hope people are largely familiar with, the idea that polyunsaturated fatty acids, or PUFAs, in fish can be quite beneficial, actually, for many things. And one of those that's in fact been shown in randomized trials and whatnot is that it's good for the heart, and in fact can sort of prevent coronary heart disease and other heart problems. But there's real concern that mercury can increase the likelihood of heart problems like coronary heart disease, right? But the fundamental problem is that the two of these things are often very correlated, because they both, a common source of both of these is fish consumption. So this would be the DAG, where you've got fish consumption leading to higher PUFA exposure, also higher mercury exposure, and those both may affect coronary heart disease. And in this example, they may affect it in opposite directions, right? So what do we do in this case? We, as in the DAG speak, right, we draw a box around these things to say we adjust for them, we control for them. So you know, in your model of coronary heart disease, yes, no, you have as two predictor variables, PUFA levels and mercury, right? So that you essentially block the confounding pathway through the other one. We can now look at the independent effect of mercury on coronary heart disease, because this backward pathway through fish consumption and PUFAs to coronary heart disease would be blocked by adjusting for the PUFAs. And the same for the effect of PUFAs on heart disease. The back pathway through mercury is blocked. So we can look at the independent effect of each of these on the outcome. The problem is that's not, how do we actually do that, right? How we actually typically do that is we have some measurement of PUFAs and some measurement of mercury, usually that has some error. So as an example, maybe we assess PUFA intake from a food frequency questionnaire, where we ask how much fish have you eaten, maybe different types of fish, all these things. And we do some kind of conversion and say, here's the PUFA levels. So that's related to the PUFAs. The amount of PUFAs you eat will affect your reporting of PUFAs on a food frequency questionnaire, but there will be some error with that, right? We do the same thing with mercury. Maybe we take a blood sample or maybe toenail samples at some point and say that's going to reflect the mercury exposure, but it's got some error with the actual exposure right here. So what we're actually doing in our models is adjusting for these things, right? We're not actually adjusting for the true, I mean, usually not, the actual true causal amount of PUFA or mercury that we really care about. So we've got some proxy of it, and those have error, right? So the question is, what happens if that error is different? And let's take as an example that you're measuring PUFAs with a food frequency questionnaire. You know, there's various data out there on how well food frequency questionnaires predict a variety of things, but it's probably not as good a predictor as, say, mercury in toenails or mercury in blood. of exposure. And so we're not fully adjusting for these things, because adjusting for these things that are predicted by the exposure do to some degree adjust for the exposure, but they do that to the extent that the real thing predicts the thing you're measuring. So how much error is there between PUFAs and your measurement of the PUFAs, actual PUFA exposure and whatever you're measuring, or actual mercury exposure and whatever you're measuring? The amount of error you've got there will reduce how well you're actually adjusting for those things, right? So I put it in a sort of dashed box because you're not doing a perfect adjustment for either of these, right? So that's fundamentally problematic to begin with, right? We have to worry about that kind of issue. But we've also got an issue if one of them really does a worse job of that, right? So let's say the PUFA measured with food frequency is just not nearly as good at capturing your true PUFA intake as mercury in toenails is at capturing mercury. What happens? Well, you don't adjust for PUFAs as well as you adjust for the mercury, right? And this leads to all sorts of problems, one of which is that essentially, I mean, the basics of this is the less well you adjust for PUFAs, the less well you've blocked that pathway. So when you're looking at the mercury effect, you're now allowing some of this backdoor path through the actual PUFAs, right? And if there's a difference between these two that is, reasonably large, so your error is much bigger here than it is here, your mercury signal is going to pick up part of the PUFAs. So what you see in your study for the effect of mercury on coronary heart disease will be a combination of the actual effect of mercury and some effect of confounding by PUFAs. And if that measurement error is so great here that you do a terrible, terrible job and essentially don't adjust for PUFAs, it's a confounded result for mercury. And in fact, the mercury may be a better measurement of kind of your fish consumption and your PUFA exposure than your PUFA food frequency. And so you can even potentially, you could in theory get protective effects of mercury because you've basically opened this backdoor path, right? So having different levels of error on different variables can be quite important in your analyses. Yeah, so that's what I just said. We'll move on. Let's look, though, how that plays out when thinking also about this exposure, the more proxy exposure measurement for things, right? So here's a study that I did a long time ago about air pollution or particulate matter and autism, looking at particulate matter exposure during pregnancy and during the 3 trimesters of pregnancy, right? This was in the Nurses' Health Study. We can just focus on the top row, which is PM 2.5. And what we found in a model that contained all 3 of these, this relates, by the way, to the extra papers I sort of suggested, which are really not required for this talk. But negative control exposures is going to come up here, and it's a very important thing that I think is worth understanding. But these are exposure levels during the 3 trimesters of pregnancy assigned by an ambient monitor thing, or rather a spatiotemporal model. They're all in the model at the same time, and we can get into why that's relevant. And we saw an association with the exposure in the 3rd trimester, but not the 1st or the 2nd trimester. So the first thing I want to just make clear, and we'll talk about, is the concept of how, in this case, the 1st and 2nd trimesters act as what we call a negative control exposure. So what's the idea behind that? The idea behind that is that if you have some variable that confounds both the that is associated with the exposure in the 1st trimester and the 3rd trimester, and also related to your outcome, right? That confounds both of them, then you can use this, you can use the results from these 2 1st trimester, 3rd trimester to assess whether this is here, whether you've got something like this. If there is if an association is not seen with a negative control exposure, in this case, let's take the 1st trimester, then this kind of confounding cannot be there for your result for the 3rd trimester, because anything that equally affects the 1st and the 3rd should result in a confounded result. So if you don't see anything with the 1st trimester, this can't be there, because if this was there, you would see an association with the 1st trimester's exposure level. So as an example, socioeconomic status that tends to affect air pollution exposures relatively constantly over time. The idea here is that this controls against these kind of time invariant factors. If your SES affects how likely you are to take folate, even folate in the first trimester, that can't confound a result that's only seen in the third and not the first, because this kind of confounding should lead to a result even with the first trimester exposure level. So instead, you're left with, it must be something like this, because you don't have a U to this. If you're only seeing the result with the third trimester and not the first, it must be that there is a differential effect there, that something's going on with the third trimester and not the first, or at least it cannot be confounded by anything that affects those two exposures equally. So in this case, how does that relate to the sort of personal behaviors? Well, if you have personal behaviors in the first trimester and the third trimester that are different, that can lead to this problem, right? So what I was talking about is U's before that affect these two equally. But if you have something that affects each one separately, all bets are off, because now you could have confounding on the first and confounding on the third in different ways and create a different result for the two exposure levels, the two exposure measurements you have. However, if you use the ambient measurement estimate, not a personal one, then again, these sort of personal factors that could affect your exposure in the two trimesters differently, right? These become colliders. So these personal factors don't affect the ambient estimate. So the idea that, let's say, a mother's behavior or someone who's pregnant in the first trimester acts very differently than in the third trimester, which is certainly reasonable to think given pregnancy and how it goes, though that could affect how often one is near one's own home or activities that they do. Clearly, personal things can change from the first to the third trimester, but those things that are changing don't affect the ambient estimate, right? So they can't confound here. Again, that's the principle we just showed earlier. The interesting thing, though, is that because of that, your personal behaviors may be quite different. It is possible that one of these does a much worse job at predicting the personal exposure, right? Now, that looks like, okay, well, you've got a different effect here than here. So maybe that can account for what we're seeing. But if it's the personal behaviors that is leading to this not being as good an estimate, then if there's really no true effect of either of these, it won't affect anything. And that was Marianthi's point, that with non-differential measurement error of these things, if it is, it will bias to the null, but that means that if there's no true causal effect, in other words, we're already at the null, there is no difference. You won't see any difference here. So using the ambient, even if the ambient is not as good a predictor of one of these exposures than the other, if there's no true effect, it's not going to cause one, and it's not going to make something look different between the first and the second. The only way that this kind of measurement error being worse here than here can make the associations with these two exposures look different is if there is actually an effect of those two exposures, right? So you might get something that looks different because of differential measurement error from your ambient to your personal at the two time points. But you only get that if there actually is a real effect going on. So a little quirky. All right, keeping an eye on the time here, running short. So let's go on. Very important points that I just want to make to summarize things, right, about types of exposure measurement error, right? Where does this come from? So I've been talking a lot about the idea that, a more proxy exposure, the further you are from the individual, the more error you're going to introduce. That's what we've been talking about, right? You might miss personal behaviors that affect exposure levels. This can happen with biomarkers too, right? And if you're really interested in what's going on in the brain, and I use a toenail as my exposure assessment, well, that's an excretion route, and I have to worry about how well does that actually predict what got into the brain, right? So that's another place where error can show up. Marianthi talked about lab measurement error. You can absolutely get lab measurement error. You have to pay attention to that and know how well the lab is assessing whatever variable you're looking at. Also, very importantly, you can get error when it's a timing error. If you can have the best measurement in the world, but if you need to know that, if the biologically relevant time period is, let's say, pregnancy, and you're measuring at 10 years old, that's a lot of error. It's not going to predict what the exposure was during pregnancy very well. So that's another source of error in your measurements. And another one that's very important is how you parameterize your exposure assessment. So we don't always think about this, but relative to the biology, you can be introducing error here too. And an example of this is, let's say these two subjects here just made it up, 24 years of exposure, intensity on the y-axis, years on the x-axis. If you sort of do an area under the curve for cumulative exposure of these two folks, the total exposure is identical, right? The total cumulative exposure is identical. But admittedly, right, the pattern is very different. So if the biology of your disease is something like silica exposure and silicosis, where every time you get exposure to any silica, it causes some lung damage, and that lung damage stays, and the more you have, the more lung damage you have, then cumulative makes a lot of sense. And the risk for these two people at 24 years should be identical because you've had the same amount of damage to the lung. But if you're instead looking at ozone and your risk of asthma, an asthma attack, the risk at year 24 is going to be much more related to your ozone, like right around here, right? Not what happened 10, 20 years ago. So cumulative measure would be wrong to summarize what is biologically relevant for asthma. And so that's another form of error. It's how well does, however you decided to parameterize this, relate to the true biologically relevant exposure. I think I saw something in the chat here. It is not that accurate. We open a backdoor path. Yes. But then but then by adjusting for PUFAs as its measurement is not that accurate, we open the backdoor path. Sorry, it's not that by adjusting for it, you open the path. It's that your adjustment for it is based on a measure that has a lot of error. So you're not actually adjusting for it as well as you think, and you're leaving the pathway open. Because when you have the actual exposure you care about, and you're measuring it with something that has error, if this error, you're only going to adjust for the true thing, as well as the true thing predicts the thing you're actually measuring. So if you've got a lot of error in this, I mean, in the extreme, if it's totally unrelated, you're not adjusting for the PUFAs at all. If it's somewhere in between, you're partially adjusting for the PUFAs, but that still allows the PUFAs to have some variability beyond what you're accounting for. And so it allows a little bit of confounding to still sort of slip through. I hope that makes sense.
Sorry, can you listen to me?
Sure, yes, I hear you.
Yes. So the idea is that by adjusting, you're trying to close the backdoor path, but as the measurement is not that accurate, you might be thinking that you are closing the door, but actually you are leaving it somehow open because the measurement is not that accurate, right?
Exactly.
Okay.
Exactly. And I mean, I put this here in terms of a co-exposure, like we care about PUFAs also having an effect, but any other variable, if you care about socioeconomic status, or you care about smoking, or you care about age, if you're measuring those things with error, you're just not blocking the path as well as you could. And so to the extent you're not blocking the path, you're allowing some statistical association to flow through it. Right. So it's true for any variable that you're trying to measure. If you've got measurement error on a covariate, you're just not adjusting for it as well as you could be, or you might want to be.
So somehow the backdoor path will always be kind of open, right? Because there's always an error associated to every measurement.
Yeah, so that's probably correct. Yes.
Okay.
You have to worry about it. Okay, so we're kind of getting late, so I don't know. Sorry. So this one is, I just want to make clear that, every time you put an exposure measurement in a model that you're working on, you are implicitly or explicitly sort of making an assumption about the relation between the actual biology between the exposure and the outcome. And so that biology may be very different. It may be that what matters is the last day of exposure, and anything prior to that has no relation whatsoever. So you don't want to count it in your exposure measure. Or it may be cumulative, like looking at silica over the years and silicosis. And so if you're getting that slightly wrong, then you have to ask, what is the correlation between the thing I'm actually measuring and the type of metric I actually want, like, sort of peak exposure over the last week or something. If there's a correlation there, you'll capture some of it, but you'll capture it with error. If there's no correlation, you have complete error and you won't see anything. All right, since I'm kind of running out of time, the next slide, this is just, it's in here. You guys, I think, have the slide, so you can work on this to sort of show yourself in a 2x2 setting. It's just a very simple odds ratio setting, how these things bias to the null. If you've got a true actual association like this, right, odds ratio of 2, you can do your odds ratio out. If you do non-differential misclassification, meaning you kind of move the same percentage of people from exposed to unexposed, or the other direction, you can play with these numbers, you will bias it to the null, and you can see that in the odds ratio. You can sort of play around with how these numbers work out. The differential, which we haven't touched on yet, we've talked mostly about non-differential, is that you're making your measurement error differently by cases and controls, or the outcome in relation to the outcome in some way. And now, depending on how that goes, you can bias in any direction, right? If you're systematically. So this was the point Marianthi and I were discussing about the difference between having more or less measurement error by your outcome. That's a little different, and that relates to the simulations Marianthi talked about and was doing, and is seeing that probably still biases to the null, which makes sense to me. So that I think that sounds right in her simulations. But that's a little different from systematically measuring something wrong by cases and controls. That is, as we were talking about, like always measuring slightly higher in your cases. And this is why, as she said, you never, if you have case and controls and you have lab samples and you send them to labs, you never want to send like all your cases first and then send all your controls, because if the lab technique sort of drifts a little bit and, let's say, goes down, then it's going to give you lower measurements for your controls than your cases, simply because you measured them later and the machines had drifted down. So that's why you want to sort of interleave cases and controls all the time, so you avoid that kind of difference. But that would be a differential measurement error, and depending on which way it goes, you can bias upwards or downwards. You can take a totally null effect, there's really no true causal association, and create one. And the example I was going to give to this, and I'll go through it quickly, but if people have questions and they don't get this, email me or put it in the chat and we can respond to them later. But it's related to perfluoroalkyl compounds, polyfluoroalkyl compounds here, PFOA, and birth weight. And there's a lot of work on whether exposure during pregnancy to PFOA affects birth weight. There were a couple of meta-analyses done on this, one in 2017 that had a whole bunch of studies in birds, and they explicitly excluded a paper by David Savitz et al. Precisely because it used a modeled estimate of exposure. And they said that's not as good. And it's true, it's not as good, it's got more error than measuring blood, PFOA in blood from a sample taken from a mother. So they excluded it. Another one, then Kyle Steenland came along later, did another one with more data and looked at sort of what was the situation, whether you included the Savitz study or not. And this was the results. When you don't include the Savitz paper, they do see lower birth weight with higher PFOA concentrations in the mother's blood. But if you do include the Savitz paper that used the modeled result, now it was huge, partly because you could use a modeled result, so it's a lot easier to do. You saw no association between the PFOA and the birth weight. This is that, getting back to that reverse causation problem that we may have. And so this was their concern, that the problem with taking a blood sample during pregnancy is that maternal blood volume changes during pregnancy and it expands, right? So what that means is if you're expanding the volume that your contaminant is in, it will look like a lower concentration. So that volume change over pregnancy can affect the apparent, it's essentially measurement error, because it's the same, you can have the same dose internally, but it will be measured lower because the volume that's in expands during pregnancy. And that was shown by Sagiv et al. That as that maternal blood volume expands, the PFOA concentration looks like it's lower. So now the problem is, if that maternal blood volume expansion is for some reason related to the outcome, in this case birth weight, like maybe because of some placental health issue, now you've got a connection between your outcome and the measurement in blood. And that thing is not related to the modeled exposure, because the modeled exposure has no relation whatsoever with maternal blood volume expansion, right? So you can use this to potentially avoid reverse causation. Now, they did it to try and figure it out. They actually did a lot of studying to say, what is the relation here? And they found about a correlation of about 0.7. So it was a pretty good model prediction of maternal blood. And they said, one of the ways we can test what's going on here is maybe look at those studies that took maternal blood early in pregnancy versus late in pregnancy, because the expansion gets much stronger late in pregnancy. So this effect should be stronger late in pregnancy. And when they in fact did that and looked at all the studies that took the samples in the second or third trimester of the maternal blood, they saw a strong effect of PFOA on birth weight. But all the ones that took it in the first trimester, or even one study before pregnancy, they saw nothing. Right. So because of time, I'll go over this quickly, but basically it was definitely different by the trimesters. Now, it's possible it's a trimester specific effect, and it's only late in pregnancy that you see the effect, but there's a strong concern about confounding here. And the modeled estimate, I mean, first of all, the Darrow paper looked at pre-pregnancy. So to the extent that pre-pregnancy continues to predict your exposures, we should still expect to see it, but maybe not, because maybe your exposures change. But the modeled estimate should be totally unrelated to these changes, how you change during pregnancy. So you should still see it there, and you don't. And just to end quickly, you have this summary. It's basically what I've shown you, but you have to be careful with biomarkers if they might be affected by the outcome you're looking at. That's an important piece here, and that these worse, more proxy estimates that have more error may avoid some confounding or reverse causation that is important to you. All right, so in the end, the important takeaways of all this is exposure measurement error can clearly bias true causal effects to the null, but can also potentially avoid certain types of confounding with implications for validity if you're using exposure that has more measurement error but is further removed from personal behaviors. Exposure measurement error can reduce the effectiveness of controlling for confounding variables, and it can be caused by many things, and that's important. Also, the timing and how you're constructing your exposure estimate. And again, if the measurements are different by case status, you can actually produce associations. All right, sorry, I think I went a little longer than I wanted, but there we go. I don't know whether to keep my slides up in case people have questions.
Yeah, that's fine. Thank you so much. That was a really great run through. We have just a few minutes left. If anyone does have questions, please type them quickly, or better yet, just jump onto the camera.
One slide, go back.
Go back one slide.
Wrong way. Where am I going now? Here. This one, or?
Yes.
There you go.
Right. I think everyone is absorbing.
I know. Sorry.
Quite a lot of information. So
yeah, and if you're not able to get it in, so is my understanding right that there is like a discussion board? So it's not just
you have a discussion board. Yeah. So folks, afterwards, if you've think about it and things come up, you can put them there, and we'll make sure to reach out to Marc to get those answers for you, or Marianthi.
Yeah, and if
I would love for our discussion board to get a little bit more active so that we can have some kind of back and forth, but and
they have access to the slides, right? Somewhere.
Yeah, well, they have access to the slides and the recording. So
great. All right. Well, yeah. So definitely, I know. Sorry, I went through a lot of that kind of quickly, but if there are questions, I'll be. Does somebody alert me? Do I need to check that chat board regularly, or will someone alert me?
We'll alert you if something comes up. Yeah.
Great. So yeah, happy to field any questions for anyone out there.
Any last thoughts before we sign off for the day? Feel free again to just jump on the camera or the microphone.
And Marianthi, I'll send you an email because we're getting together on Thursday, right? I don't know if she's still on, but if you're on, Marianthi.
All right. Thank you so much, both Marc and Marianthi. This was I think, a really great session. So we will see everyone next month. Anna, did you want to give us an announcement about what's coming up?
Yes, so tomorrow we will have the second applied session on misclassification by Cristina Villanueva, giving an example of water pollution. And then next month it will be kind of exceptional because there will be two sets of sessions. First one on ethics for research and then another one on confounding and selection bias. So see you all tomorrow or next month. Thank you.
And it looks like somebody, Aria, did you want to ask a question? Okay.
No.
Right.
Okay. Perfect.
All right.
No.
Thank you all.
All right, thanks,
Thank you.
everybody.
Thanks, Mark.
Bye.
Bye.